Yeah, the back of his head will be
Turn around fast.
Alright, so we did say, we tracked through our energy conversions in a hydroelectric plant last time, and we did say that the starting energy was the gravitational potential energy stored in the reservoir, right, stored in the water. So the maximum amount of electrical energy we can get would be the amount of potential energy that that water is losing. So we're basing this whole thing on our change in potential energy formula. Okay, questions on that? Great. And this is something that you might be expected to derive yourself. Okay, so the starting place is potential energy, since that's the form of energy that the water that we're storing in the reservoir. Now, we typically want power. So we do know that power is the rate at which energy changes form. Okay, so I need to care about that. So power would be the change in potential energy divided by how much time it takes to do that. Or, right, mg delta H divided by the amount of time. And then we're just going to do a little tiny bit of substituting around of things. It's kind of difficult to know what mass of water we're dealing with. It's a little less difficult to know what volume of water we're dealing with. So we know that density, and the symbol for that is it's a Greek letter rho. When I write it, it looks like a lowercase p, but it's not. Density is mass over volume. So mass is density multiplied by volume. So I'm going to substitute density times volume in for mass. I'm just going to move down here. Did I do all right? Yeah?
So you're just making sure P means this.
Yeah, so I mean density, not momentum, right? I mean density. Right, and I'm kind of done. So if we're 100% efficient, the electrical power we can get from a hydroelectric plant is the density of the water, right, times the volume times gravity times the change in height of the penstock divided by how much time. But that's kind of weird. We usually stick these two things together, right? And then what we're talking about is the rate at which water is moving through the penstock, right? The volumetric flow rate. We usually have those two terms together as a single variable, and that's it, right? So like that's our expression for finding how powerful a hydroelectric plant is. The density of water is something that just as like a science person you should know. I think, I actually can't remember if that's something IB usually gives to you or not. The density of water is like 1 kilogram per liter. So if we have a volumetric flow rate in liters per second, then that's great. Then that's the value for density that we want to use. So let's look at one example of using that expression together right now, and then I'll have you guys in your U4 just do 1 or 2 more examples. China has put a tremendous amount of money in the last 10 or 20 years into building all of our types of power plants. Right, they've built some of the world's largest hydroelectric stations, some of the world's largest coal plants. So this is a real one that I think is in operation now, the Changheba plant. It's probably finished by now. And at the time when I wrote this problem, I found that it was supposed to be a 2,200 megawatt plant. Is that powerful?
Yeah.
That's very powerful. That's 2.2 gigawatts. That's very powerful. And I don't know exactly what the drop in water height can be, but let's just say it's 150 meters. I want to find what volume of water has to flow through the turbine each second. All right, so our starting place will be our new expression. Did I get it right? Yeah? All right. Not one that I necessarily have memorized. So the density of water we said is 1 kilogram per liter. Now, is that a good unit for me? It's probably fine. That'll just mean that my answer is in liters per second, right, which is fine. So 1 kilogram per liter. We want to find the volumetric, I should isolate for the volumetric flow rate first. All right, Alright, so I'm going to do the power divided by the density times gravity times the drop in height. That's better. Alright, so our power is, that they're claiming, is 2,200 megawatts. I do want to change that into regular watts, so I'm just going to say 2,200 times 10 to the 6th. The density is our 1 kilogram per liter. What's G? Been a little while, right? Been a little while. 9.81. And then 150 meters was the drop we were going to use. Alright, so that should give us the number of liters each second that need to be flowing through our penstock and passing our turbine. It's going to be a lot. It's going to be a lot. Oh, it's nice to have a 1 in the denominator. We also get 1.5 times 10 to the 6th liters per second. So 1.5 million liters per second. It's a lot. Yeah, it's a lot of water. A lot of water. I would be almost positive that they have multiple turbines, like maybe even like 20, 40 turbines, right? But that would be the total amount of water. Amanda? Should I explain it in units or canceling? All right. So power is measured in watts. Really? Yeah, sure. So power is measured in watts. A watt is a joule per second. A joule is a Newton meter. Can I stop there? No. A Newton is a kilogram meter per second squared. I think I even need to go down here. Kilogram meter per second squared, but I still have this meters and this seconds. So a watt, somebody yell at me if I do this wrong. A watt is the same thing as a kilogram meter squared per second cubed. Did I get that right?
Per second.
No, no, I think I did it right. I think I did it right.
Yeah.
The denominator and the numerator can just get thrown into the denominator. Yeah, no, I think I did it right. I think it's seconds cubed. All right. Now, so what else do we, so that's what would go here. Kilograms meters squared per second cubed. The 9.81 is obviously meters per second squared, and then this is just meters, all right? This was kilograms per liter. Yeah, all right. So kilograms are gone, right? All right. Seconds squared, seconds cubed. So these seconds squared gets rid of 2 of those, and I'm left with the single s. All right. And then I got meter squared here, meter squared there. So I've got 1 over seconds in my denominator, and I've got 1 over liters. I'm sorry, 1 over seconds in my numerator, 1 over liters in my denominator. So I think that gives me meters per second.
Yeah.
Are you glad you answered? You are glad.
It makes more sense.
Okay. All right. Good. Good. Yeah.
How, like, all this water is replenished by rain?
All this water is replenished by rain, yes. Now, are they ever going to be doing 2,200 megawatts? Probably not, right? Probably they can, but then you're right. If they do that for a few hours or a few days, they're not going to be able to do it like beyond. They're going to run out of water. Yeah, so it does get replenished by rain, correct. Mary. All right, other issue. So let's move on to another example. I picked this problem because I know like New Jersey has Palisades, but this is not in New Jersey. But I found a Palisades power plant which had a total amount of electrical energy 6 years, 7 years ago of 509 million kilowatt hours. First thing I want you to do is find the average power that this plant developed in that year. And then, once we have the average power, then we'll use this new equation to find out what the average flow rate of water was. In your foursomes, all right? In your foursomes.
Average per day. Yes. Per year. Average per year.